Well, sorry I couldn't be with you in class today, but we'll do the best we can from a distance. I'd like to talk about geometric sequences. You were introduced to those in the homework last night, and one of the sequences that you were given was this, and we know it's not an arithmetic sequence because the differences, 3 to 6 is a jump of 3, 6 to 12 is a jump of 3, or of 6, which is not constant. We have a jump of 12 here. Therefore, with not a constant difference, we know this is not an arithmetic sequence. However, if we take a look at the ratio, and the way we can do that is, if this is our first term, second term, third term, fourth term, etc. here, if we're writing them vertical and pretend like we're in a spreadsheet, and if we take the ratios, 6 divided by 3 is 2, 12 divided by 6 is 2, 24 divided by 12 is 2. We notice we've got a constant ratio going on. You will all, I'm sure, recognize that is the function family that we call, you're right, exponential. Exponential has the equation a times b to the n, or b to the x, where our variable is in the exponent. And what we're going to do is learn how to, given a geometric sequence right now, we're going to learn how to translate that into the exact exponential equation. Now there's a couple ways we can go about it. My favorite way is this. We know that a is the starting value, and since it's the starting value at time 0, when n is 0 or x is 0, a actually turns out to be our y-intercept as well. So b, as we know, is the rate of change, and you'll remember that the exponent, x or n in this case, is the number of times that rate of change gets applied. So what we do is we say the starting value is the y-intercept. What is the y-intercept of this graph? Well, the y-intercept is where the x or n is equal to 0. So if we come back up 1, we're going half, half, half. So this is going to be 1.5, or 3 halves. That becomes our a. So over here, for the a, we write 1.5, and then times the rate of change. Well, we can see what's happening. The rate is doubling each time, so our rate of change, the base of our exponent, is 2. So whatever our constant is, that's what this b will be if the x's are going up by 1s, which on sequences is always the case because it's just the number of the sequence. So the first, second, third, fourth, it will always be whole numbers going up by 1s. Now, what do we do for the variable? Well, you'll notice if I put a 0 in here, a 0, 2 to the 0 is 1. 1 times 1.5 is 1.5. If I put a 1 in here for the exponent, 2 to the first, I get 2 times 1.5 is 3. So all this is just n. There is my nth formula. So the value of the variable here is going to be equal to 1.5 times 2 to the n. Now some of you who don't like to go back to that 0th term, that y-intercept or starting value, you might just say, I want to just take this first term and go from there. You can do that. You can make it the a. 3 times, this is still going to be a constant ratio of 2. But now you'll notice, if I plug a 0 in here, I get a 3 out, not a 1.5. And when I plug a 1 in, I get a 6 out, not a 3. And when I plug a 2 in, 2 to the second is 4 times 3 is 12, not 6. But if I adjust my my exponent here, you'll notice that I end up with n minus 1. These two are equivalent. And we can prove that by if we, let me see here. Two to the n minus 1 is 2 to the n. You'll remember when you subtract, it's divided by over 2 to the first. So n minus 1 times the 3. And that is the same as 3 over 2 times 2 to the n, which is what 3 halves times 2 to the n. So they're the same. So you can go either way. You can either go the 0th terms times 2 to the n, or the first term times 2 to the n minus 1, and this n minus 1, you adjust it back to account for the fact that we're starting with the first term, not the 0th term. So there is your approach to getting the nth formula.